what Abhijit said, please ask lots of questions. I hope there'll be lots of questions. Yeah. So this talk will be mostly based on a paper which I wrote last year together with Leonardo Rastelli and Shinan Zhu. And here and there, I'm also going to mention some connection to some work in progress with Simon Caron Ulot, again Leonardo, and also David Simons-Duffin. Okay, so what is the big picture? What is the sort of the motivation for this work? Somehow the underlying question is a little bit vague, but I'll try to make it a bit more precise during the talk. And so the underlying question is somehow what is the right basis for the conformal bootstrap? In the conformal bootstrap, we use various bases depending on various techniques depending on the specific question we ask. So there's these different approaches. For example, there's the
sorry, Dalimil.
Yep.
Sorry to interrupt you. I think perhaps your the chimes are on your side, because yours is the only microphone that is on, and we are hearing the chimes, entry and exit chimes.
Sorry,
like this one.
What is on?
There is some sound coming when people are joining. I don't know. Is it just me or everyone is hearing them?
I don't hear any sounds like that.
Oh.
So it's probably.
I see. Okay. Sorry to bother you.
Yeah.
Go ahead, please.
If it keeps happening, maybe
maybe just on my side. I don't know. This was not happening before, but yeah, please.
Okay. So yeah, there are at least these three different approaches to the bootstrap. In some sense, the oldest one is the numerical bootstrap, pioneered by these authors. And well, in numerical bootstrap, the basis in some sense is the expansion of the crossing equation around some Euclidean point. Usually we call it z equals z bar equal 1/2. It's a crossing symmetric point. Yet another approach to the bootstrap is the analytic one, the analytic light cone bootstrap, or sometimes equivalently the Lorentzian inversion formula, which uses the expansion around a pair of light cones. And yet another technique is this Polyakov-Mellin bootstrap, and it's a little bit unclear how this is related to the other two and what exactly it means. So somehow one of the motivations goals for this is to make maybe the connection between these approaches a bit more clear. In particular, I'm going to have something to say about the status of the Polyakov-Mellin bootstrap. But that's somehow the question. What is the right basis for the conformal bootstrap? And maybe more concretely is we're gonna ask the question, but not quite answer it, but we're gonna ask it, is how do we systematically derive bounds on holographic CFTs? So the bootstrap has been spectacularly successful in constraining conformal field theories with small central charge, like for example, the 3D Ising model, the critical exponents at a remarkable precision thanks to a numerical bootstrap. So we also know that the bootstrap applies to holographic CFTs thanks to the ADS CFT correspondence. So it's very natural to try to ask whether we could find as strong constraints on holographic CFTs with large central charge as we do on small c CFTs. And so far we haven't really been able to do that. It looks like with what we've been able to do so far, essentially every effective field theory in ADS gives us a consistent solution to crossing. So it would seem that at small c, the numerical bootstrap is more constraining than at large c. But perhaps we just need to think about a problem a bit harder and find the right basis to make progress. So that's the motivation. And let me jump into setting up the stage for the rest of the talk, introducing some notation. So okay, maybe let me try to see if I can make a pointer. Yeah. Okay, this works pretty well. Maybe okay, so the setup for the rest of the talk will be the crossing equation for the 4-point function of scalars. And I chose these to be not quite identical scalars, but for two pairs of complex conjugate scalars, phi bar. Phi bar is the conjugate of phi. So phi bar, and this we're going to write it as follows in the usual way, where we take out some conformal covariant prefactor and get a function of two cross ratios, z and z bar. So these z and z bar are the usual cross ratios. I'm just going to write them out. And this is usually called U, this is called V, and this would be the same thing as above, just with 2 and 4 swapped. So that's the 4-point function. And how do we get a crossing equation? Well, we just expand this 4-point function in two different OPEs. This is the S channel OP. Whoops, that's not what I want. This is the S channel OP, and this is the T channel OP. The reason why I chose not identical scalars, but complex phi and phi bar is that both the S and T channel OP are going to contain all spins, so not just the even spins, as would be the case for identical real scalars, but both even and odd spins. So how this is a beautiful and mysterious equation, the crossing equation, and it's really hard to analyze. In some sense, it's an infinite set of constraints for infinite limit unknowns. These unknowns are the OP coefficients and the scaling dimensions of the operators, and the constraints are labeled by the values of the cross ratio z and z bar. So how should we think about it? Well, one way to organize our thoughts is to talk about functionals. So in the rest of the talk, what I mean by functional is just functional acting on functions of two cross ratios. So omega is a functional which sends f to the complex numbers, and because the crossing equation is symmetric under switching z and 1 minus z, I can assume without loss of generality that the functional is crossing antisymmetric. So then I just take this functional and I'm going to apply it to the crossing equation. And what I arrive at is this equation at the bottom. It's just the sum, but now we have just one constraint instead of infinitely many constraints. So that's the equation. Here it is again at the top. And in some sense, all of what conformal bootstrap is the search for specific functionals. Like we ask some question, like for example, what is the bound on this particular dimension in a specific theory, and to solve the problem means to find a functional which answers the question for us. And the goal for this talk is to identify some useful basis for the space of functionals. And for now, the goal for now will be for me to explain what I mean by useful. So it's not exactly clear a priori what the useful basis, what it means to have a useful basis. So let me talk about that now. Well, it's important to note that these coefficients are all non-negative because there are some absolute value squares of complex numbers. So just imagine, I mean, this function doesn't exist, but just imagine that we found a function which would be positive on all conformal blocks, on all these. Maybe I didn't say, but these G's are conformal blocks. So imagine that we have a function which is positive on all conformal blocks. This would imply that no unitary CFTs exist because we would have a sum of positive numbers equals 0. So that's impossible. Okay, well, we certainly know that some CFTs exist, so such a functional doesn't exist, but we're going to sort of try to successively weaken the constraints on the functional to see what we end up with. But the reason why CFTs exist is that there is at least one CFT which always exists, and that's mean field theory, which is the same thing as a free theory in anti-de Sitter space. And in that case, the OPE contains the identity. So the sum over O's contains the identity. These so-called double trace operators, which are labeled by a pair of non-negative integers n and l. These double trace operators have dimensions 2 delta phi plus 2n plus l. So okay, so this is somehow the most fundamental, simplest solution to the bootstrap equation. So certainly every functional needs to be compatible with the existence of this solution. So somehow the best case scenario, assuming that the mean field theory is the only theory that exists, would be to have a functional which looks like this. So to have a functional which is non-negative everywhere except for the locations of the operators present in this OPE, in the OP of the mean field theory. So it follows that it would have to have double zeros on all the double trace dimensions for all the spins. Now, we don't certainly in low dimensions there are other unitary CFTs than the mean field theory. So this function also generally doesn't exist, but there are situations where it could exist. One example would be higher dimensional CFTs. So we don't really know whether there are interacting unitary CFTs in dimension more than 6. So you could imagine that you could prove the non-existence of CFTs in dimension greater than 6 by exhibiting such a functional. If you can find a functional which is non-negative everywhere except for the mean field theory, then you would prove that mean field theory is the only solution to crossing and that there are no interacting CFTs. So we haven't quite been able to do that, but one case where actually we found such a functional is in the context of n equals 4 super Young males at infinite central charge. So it is a theorem, thanks to the existence of this functional, that the only n equals 4 SCFT in 4 dimensions with strictly infinite central charge is mean field theory. I mean, we of course know that super Young males with infinite C is mean field theory. It only starts deviating from mean field theory as you take C less than infinity. So in some, it's a slightly trivial theorem, but perhaps it could be used as an inspiration for some higher D explorations. All right, so this, are there any questions so far, maybe? Okay, looks like there are no questions yet. Let's see. So let me continue. So this somehow leads to the notion of the basis for the space of functionals that we identified in our paper with Leonardo and Shinan. So the constraints that a functional omega has double zero on a given double trace, the double trace labeled by n and l, is just these two equations at the top. I need to get used to this. These two equations at the top, that the first equation just says that the functional vanishes on the double trace conformal block, and the second equation says that in fact it's not just a simple zero, but it's a double zero. So the basic idea for constructing what the basis is that we are just going to violate these constraints at a single double trace. So the basis consists of functionals which have double zeros on all except for one double trace conformal block. And it turns out that there are two different ways that you can violate these constraints locally. One is the beta type and the other one is the alpha type. So we have two infinite families of functionals. The beta type functional is a functional which has double zeros on all the double traces except for one, and there it has a simple zero. So these are the equations for the beta functional. So the first point over here says that the functional vanishes on all double traces. So I should say that the betas are labeled by a pair of by the double traces essentially, n and l. And n is the twist, and l is the spin of the double trace. So the beta type vanishes on the double trace, on all double traces, and has a double zero on all except for one double trace. So precisely when n is equal to n prime and l is equal to l prime, we get a simple zero. So this is what the beta functional would look like when it acts on conformal blocks. So here I'm acting with a beta and an L on a conformal block of the same spin. L. So you can see here is the simple 0. That's when n is equal to n prime. And there are double zeros everywhere else. Okay, so and similarly, we can construct. I haven't told you how to construct them, but I may eventually tell you how to construct them. But there is this other type of function, which is the alpha type, and that one is non-vanishing at a specific double trace. So again, it's labeled by the double traces, but now instead of vanishing on all of them, it's non-vanishing on one double trace, and it has a zero derivative there. So it would look like this. There are double zeros everywhere except for one double trace, so there is non-vanishing. Okay, so
is the alpha type positive everywhere except at its zeros?
Yeah, positivity is tricky. The way I drew these things, it looks like positivity is kind of trivial, but it's more complicated. So I'm not sure if I'll discuss positivity. So yeah, the function, these functions are uniquely fixed by these constraints, but by how they behave on the double traces, and then you can ask, are they positive where they should be? Like, are they all, is the second derivative always positive at all the double traces, say above 2 delta phi? And the answer is no. So that's somehow what makes the problem interesting. Like if all these functionals were positive, say above this gap, above the simple 0, then essentially all the bootstrap ones would be trivial. You could use them to show that the mean field theory saturates the bound, and but maybe by taking some linear combinations you could get something non-trivial. But somehow in my opinion, part of the richness of the bootstrap is that this basis doesn't have the obvious positivity properties. Like only if you start taking some non-trivial linear combinations of these alphas and betas do you get nice positive things. And I'm going to try to discuss that a little bit later on. But for now, yeah, the answer is no. The positivity properties are quite obscure. The only thing which is true is the structure of double zeros. On the other hand, in 1D, I should say that all of this project and the construction of these alphas and betas was inspired by my and Miguel Paulo's work in one dimension, where we constructed these alphas and betas, except now they don't have any spin label. They are just labeled by the twist because there is no spin in 1D. And in that case, the positivity properties were quite easy. So for example, the leading beta, the beta 0, would be positive everywhere above the gap, and you can use it to show that mean field theory saturates the bound. In that case, it was the fermionic mean field theory. And here I'm talking about bosonic one, but maybe that's not so important. But somehow, yeah, in 1D, positivity was quite clear, and in higher D, you need to work harder to understand it. The 1D functionals of these alphas and beta types were also applied to modular bootstrap in my paper with Tom and Leonardo. And we noticed, so in that context, we noticed that you can use the beta 0 functional to solve the sphere packing problem in 8 and 24 dimensions. So this sphere packing problem was solved by Vyazovska in 8 dimensions in 2016, and in 24 dimensions by her and some collaborators. And it turns out that the technique that she used is essentially constructing this beta 0 functional, applying it to the modular bootstrap, even though that's of course not how they thought about it, but we realized that once you have these functionals, I mean, you need to work pretty hard to construct them, but once you have them, you can apply them to all these cool problems like the sphere packing problem.
Dalimil, could you also say what is the action of these alphas and betas on the identity?
Yes. So the beta, you see, you can apply these functionals to any crossing symmetric correlator. You can apply to mean field theory, which would have identity in the OPE, and also only double traces besides identity. So just by requiring consistency of these functionals with this correlator of mean field theory, you would find that beta vanishes on identity because each beta kills all the mean field theory operators. So it also needs to kill identity, otherwise the sum rule wouldn't be consistent. And for the alpha, well, alpha is essentially, when it's acts on identity, it's minus the OP coefficient of the double trace. Right? You get a sort of sum rule where only identity and the NL double trace contributes in that case.
Okay, thank you.
Okay, any other questions? Okay, so maybe that was a bit abstract. Well, definitely was a bit abstract. And if you've never seen these alphas and betas, you're probably asking what the heck is going on. So let me try to reverse justify why it's useful. And the answer, one answer is that you can use these functionals to do holographic bootstrap, and that's a subject of some ongoing work with Simon, Leonardo, and David Simons-Duffin, which hopefully is going to appear soon. So the basic idea is that the structure of double zero, so the functionals of the alphas and betas, ensures that the contribution of double traces is suppressed, and even when they're approximate. So when you have an operator close to the double trace value, because there's a double zero, the contribution of the operator is suppressed. So why is that useful for holography? Well, let's think about the OPE of this correlator 5 bar in some holographic CFT. Well, first of all, what does it mean to have a holographic CFT? It means that you have some expansion in a parameter, which is 1 over central charge. 1 over c goes to 0. And as c goes to infinity, you just get mean field theory. And then you have some expansion in 1 over c around mean field theory. So you have some light contributions to the OPE, which contains identity, the double trace operators, and also some single trace operators, which these also couple with a 1 over c proportional coupling. So these operators in red are supposed to be the light single traces. Also, I should say double traces receive some 1 over c corrections. So that's another 1 over c contribution. And besides that, we only have the heavy operators, which for the purposes of holography, we assume have twist greater than some delta gap, where delta gap is some large number. And all the other contributions like higher traces and higher corrections to double trace anomalies and so on are suppressed by high power of c, so 1 over c squared. Now, suppose that we take a functional omega, which is of the following form. It is some linear combination of these alphas and betas. Maybe it's a finite linear combination, or maybe it's an infinite one. But what I'm going to require is that the n label, so the twist, is bounded by some n0. So that's sort of to ensure that these alphas, these alphas and betas do not really probe the heavy operators too much. Well, anyway. So and suppose, in addition to that this functional is non-negative for all the twists greater than delta gap. And okay, let's take this functional and apply to the solution to the crossing equation in this holographic some holographic CFT. Well, you find the following equality. At order 1 over c0, things cancel precisely because of the question that Abhijit asked. The action on identity always compensates the mean field theory at the leading order in 1 over c0. So the leading order to the sum rule comes from 1 over c. And there's a contribution of light operators, which just comes from anomalous dimensions of double trace operators, and also from the single trace operators, the light single traces. And I can put the rest on the other side, and the other side then contains all the contributions of the heavy operators. And the rest is suppressed by 1 over c squared. Now the point is, because we assume that this omega was positive on the heavy operators, the right-hand side is sign uniform at the leading order, which imposes an inequality on the left-hand side. And the left-hand side is completely computable from the low energy data, because it's just some of low anomalous dimensions of double traces and single traces. So this is precisely what it means to have this is precisely the kind of object which is computable at low energy, because these alphas and betas only receive contributions from the the low-lying anomalous dimensions and not from the high-lying ones. So yeah, so that's the idea, that you get some inequality type constraint on the low energy data by requiring UV completeness.
But Dalimil, I have a question. So the way the contribution, the way the application of the so the anomalous dimensions of the double trace operators are determined by insisting that it produces the contribution of the single trace operator in the dual channel, right?
Yes.
So
right.
why is it that application of the functional just doesn't kill the left-hand side itself? Because they are supposed to be crossing symmetric.
Mm-hmm. That's a great question, and the answer. I mean, I don't really want to go into too much detail, but the answer has to do with the Reggie behavior. So it turns out I may mention it a little bit later, but essentially the validity of the sum rules coming from the alphas and betas requires the good non-perturbative Reggie behavior. So in non-perturbatively, we know that the correlation function and the Reggie limit are bounded, but essentially in this convention, the relevant Reggie limit is the U-channel Reggie limit, and we know that in that case, in the convention I'm using, the correlator is bounded by a constant. But if you just take some random exchange, say spin 2 exchange or spin greater than 0 exchange, with a diagram, say crossing symmetrize it, then this is not going to satisfy the property, which means that the left-hand side is not going to give 0. Yeah. Okay.
I see. Okay.
Yeah. Yeah. Basically, the answer is to say when you just take a graviton exchange, crossing symmetrize, the statement is that this is non-zero. Left-hand side is non-zero. So this is in contrast with the usual Bootstrap. Like if you just take crossing equation and evaluate it as some value of z and z bar, you would get 0, because of course the crossing symmetric sum of exchanges is crossing symmetric. So if you just evaluate the equation at fixed z and z bar, you will get 0. But well, these functions are constructed as some integrals which probe the Reggie limit, and that's why the left-hand side is non-zero in general.
Thank you.
Okay. Any other questions about this? I mean, this is all I'm going to say about it right now. Originally, I wanted to have the entire talk about this, but we are still we still need to brush up on some details, and I wanted to wait with explaining the details to some future talk. But yeah, if there are any general questions about the logic, please ask.
Okay, maybe I can ask one more question. Do you have this functional that is positive for all for twists greater than delta gap?
Yep, yeah, there are, yeah. So the individual alphas and betas are not like that, but we do have some examples.
And in that case, what is delta gap? Or you would rather, if you rather not talk about it, it's fine. What is delta gap?
Well, I guess we have an example with delta gap being 2 delta phi, which is the twist. You know, I mean, an example of this function also appeared in the Mellin Bootstrap paper, where it's like a twist gap extremal functional, where the twist gap is 2 delta phi.
Okay.
So yeah, such functionals exist, and but you know, for holographic applications, it's not that important what delta gap is, as long as it's large.
Right. But delta gap also cannot be smaller than 2 delta phi, right? I would imagine.
That's, well, the upper bound on delta gap cannot be smaller than 2 delta phi, because there is a theory, namely mean-field theory, with delta gap you can go to 2 delta phi. But yeah, but of course there are theories whose gap is smaller than 2 delta phi.
Yeah. Okay.
Hello, Dalimil. This is Rajesh.
Oh, hi. Hi, Rajesh.
Hi, are you saying that there can be many functionals with this property and you'll get many constraints, or do you think that there is one functional, or you said suppose this is 0, so do you what is the expectation or your result, or are there many constraints, many sum rules, or
I think so, yeah. So far it looks like the situation is kind of similar to what we have in the like low central charge numerical bootstrap, that there are sort of there's a large space of functionals, and there is sort of a complicated space of positivity constraints, and you just need to work maybe either numerically or analytically and try to find the optimal constraints in this space.
Okay. All right. Thanks.
Okay. So now that I told you why we are excited about these functionals, let me tell you where they come from. I mean, I haven't really explained, I didn't really show to you that they exist or anything like that. So let me give you some evidence that they exist, and well, more precisely tell you really how to get them. So the answer is that they come from a dispersion relation. And they come from the conformal dispersion relation that was recently derived by Simon Carnot and Dean Carme, and that's a relatively complicated formula. So let me first sketch the logic in a simpler example, which is a single variable dispersion relation. So the full dispersion relation is a 2-variable dispersion relation for both Z and Z bar. But for now, let me just explain how the argument would run in the single variable case. You can think of this as like a 1D bootstrap setup where we have some 4-point function on line, and we write it like this. There is just one cross ratio. We have G of Z, and again we can expand this in the S and T channel OPEs. And we'll just write down the simple Cauchy dispersion relation for G of Z. I should say that this is a similar kind of dispersion relation also appeared in this paper by Agnese, Parijat, and Tobias. It's a dispersion relation based on a single discontinuity rather than double discontinuity. So let's just write down a dispersion relation for this function G of Z. So we start with a formula here on the left. So we write G of Z as a Cauchy integral of GW with the usual PO, and so we integrate in W, and then to get this to dispersion relation, you just need to pull the contour. You pull the contour from the circle to the cuts. So you end up with a pair of contours that look like this. Did I do this right? Yep. So you find that you can split the 4-point function into a sum of 2 parts. The first part, so the G of GS, just corresponds to the left contour, and the GT corresponds to the right contour. So somehow the left contour wraps the S channel cut, and the right contour wraps the T channel cut. And here are the formulas for GS and GT. GS is just the integral from -infinity to 0 of the discontinuity of the correlator. So I read this as the S channel discontinuity because it's wrapping the S channel. And GT is this integral, which can be written as this in this form. So it's an integral from 1 to infinity over the T channel cut, again, of the discontinuity of G over that cut. So far I've explained this part of the formulas. And well, what does it have to do with functionals? What this has to do with functionals is that you can observe that GS is actually holomorphic around the T channel. So the full correlator has some power law or some branch cut both around the S and T channel. But this split kind of isolates the discontinuities. The GS only has a discontinuity around the S channel and and is completely holomorphic around Z equal 1. You can see just by looking at this formula. So here W is integrated from 1 to 0. So if Z is around 1, which is the T channel cut, there's absolutely no singularity in Z. W stays well away from 1. So you can just take this and expand it around Z equal 1. And this is what you get. So what I'm actually doing here, I'm expanding this formula in conformal blocks, in T-channel conformal blocks, and it is precisely the double trace conformal blocks, well, conformal blocks with dimensions 2 delta phi plus n, which are holomorphic. So these guys, these conformal blocks, provide a basis for holomorphic functions. They're just like powers of Z. And the coefficients of this expansion are precisely the functionals. So this is the prescription. To get a functional omega n, I take GS and I expand it around T channel. And I can do that because the discontinuity of GS around T channel is 0. And similarly for GT, I can see that GT is holomorphic around the S channel. So I can expand it in S channel double trace conformal blocks. And find some coefficients, and the coefficients are precisely the functional. So here's a way to write it more compactly. I combine this equation for G as a sum of GS and GT with their expansion in double traces, and I get this. So the statement is that the correlator can be expanded as a sum of double trace S and T channel blocks. The first part, the S channel blocks, come from the GT, and the second part come from GS. So the first part is completely holomorphic around S channel, the second part is holomorphic around T channel, but the first one reconstructs the T channel discontinuity, and the second part reconstructs the S channel discontinuity. And the coefficients are uniquely fixed by this procedure. And you can really think of them as functionals acting on G. So somehow these functionals, omega n S and omega n T, are dual to the S and T channel conformal blocks. This formula using the contour integral actually gives you a concrete prescription for what the functionals are as a contour integral in a complex plane, just by sort of expanding this Cauchy kernel in conformal blocks. And as a consequence of this formula, you find that that these orthogonality relations are satisfied. That somehow omega ns is dual to the S channel double trace conformal block, and omega nt is dual to the T channel double trace conformal block. So I'm just talking about these equations. So it's these omega n S and omega nt seem act kind of similarly as the alphas and betas that I was talking about previously. It's just that now the omegas have simple zeros. So the omega ns has simple zeros on all the T channel conformal blocks and has a simple zero on all but one S channel conformal block, and vice versa for the omega t. Does this roughly make sense, or was there? I mean, I hope to have conveyed the general idea. Do you guys have any questions about?
Yeah. So Dalimil, the contribution of the arc, is that sufficient?
Yeah,
I mean,
great question, and that's I guess again is related to the Reggie behavior. You can think of the Z goes to infinity as some sort of high energy limit, some kind of 1D version of the Reggie limit, or maybe the chaos limit. And you can neglect it. Well, you can neglect it assuming the G decays sufficiently fast. If it doesn't, then you need to do subtractions. But I wanted to avoid talking about subtractions as much as possible in this talk. Essentially, what you have to do is that if the Reggie behavior is not sufficiently good, these individual omegas are not well-defined functional. Like they don't give you consistent sum rules, but some linear combinations of them will. Like you can sort of do the subtractions at the level of the functionals. Does this answer?
Okay.
Any more questions? Okay, if not, let's go back to this very busy slide, but don't be scared, because it's just redoing the previous slide for the in the real case, for the case of the full dispersion relation in 2 variables, and that's going to give us the alphas and betas. All right, so we just need to replace g of 1 variable with g of 2 variables, z and z bar. And now the role of discontinuity of G is going to be played by the double discontinuity. You can think of the double discontinuity as the double discontinuity, first in Z bar and then in Z. It's like disk. First you apply this Z bar, then you apply this Z, and you get what's usually called the double discontinuity. And very nicely, Dean Carme and Simon Caron-Uot gave us last October a dispersion relation based on the double discontinuity for the conformal correlator. So they explained, starting from the inversion formula, that you can decompose G as a sum of 2 parts, GS and GT. And now, so I'm using the U-channel inversion formula just to orient yourself. In their paper, they were using the S-channel inversion formula. So they would sort of decompose G as a sum of G2 and GT and GU. But here we are using the U-channel inversion formula, and we get a contribution from S and T-channel D-disk. So that's literally what GS and GT are. GS comes from the S-channel double discontinuity. So it's the contribution to the C delta J function made into a correlator. I mean, the part that, so yeah, GS can be written as some double integral of the S channel D disk over this region. This is just one of the Lorentzian light cones of some kernel. So the kernel is a function of 4 variables. Z and Z bar is what sits outside, and W and W bar are being integrated. And we are integrating both W and W bar over this left branch cut. And similarly, GT is a completely symmetric integral, but this time of the T-channel double discontinuity. So W bar run from 1 to infinity. That's just another Lorentzian diamond. The kernel is the same as before up to crossing, and this kernel was fixed by Dean and Simon in the form of some it's some elliptic function of a complicated ratio of Z bar and W bar, but it's a very beautiful formula. Like, I didn't want to write K here because it looks kind of horrendous, but once you sort of become friends with it, it's an amazing. It's an amazing formula. Now, okay, how do we get functionals out of this? So in my paper with Leonardo and Shinan last year, we noticed that the analogous property as we had before in a one single variable case holds here too. So the property is that if you take GS, it has a vanishing T-channel double discontinuity, and similarly the GT has a vanishing S-channel double discontinuity. This is not really obvious if you look at Dean and Simon's paper, but we sort of had a slightly different way of looking at things, and from our point of view, it came out. So I won't be able to explain in more detail why this is true, but let me just say that there is a contour manipulation of the dispersion relation which makes this property manifest. So d disk T of GS is 0, and similarly for d disk S of GT. This means that you can expand, say GT in a complete set of conformal blocks which have a vanishing S-channel double discontinuity, and this is precisely the double trace conformal blocks. So GT, that's the green part, can be expanded using double trace conformal blocks and derivatives of double trace conformal blocks, because both of these. This is precisely the complete set of functions which which have a vanishing double discontinuity around the S channel. So this the double trace conformal block is holomorphic, so even the single discontinuity vanishes, and the derivative of a conformal block is not quite holomorphic there. There's a log, but well, one discontinuity kills the log, and the second discontinuity kills the rest. So okay, so our way of rewriting the dispersion relation is the following: that GZ is a sum over all double traces of the following 4 factors. First line coming from the S channel and the second part coming from T channel. So you can think of this equation as saying that the S channel and T channel double traces and their delta derivatives give you a basis for the space of correlators. And these coefficients are uniquely fixed, again, assuming some Regge behavior. So maybe I'll avoid talking about Regge behavior for now, but there's an important part of the story related to that. Okay, and the coefficients are precisely the alphas and betas for the same reasons as we had on the previous slide in a single variable case. Specifically, you can define these crossing antisymmetric functionals, which is a difference of alpha S and alpha T, beta S and beta T, and then they satisfy the equations which I used earlier to introduce the alphas and betas. I mean, these equations are, yeah.
Sorry, the disk Z and disk Z bar, it's clear that they commute?
Disk Z and disk Z bar? Yes, they commute. Yeah, you can yes, you can just write, you can write it out as sort of, disk Z.
Sorry, yeah, I think I get it. Yeah.
You write it out as a sum of 4 terms.
Yes, sorry.
And you see that there's a complete symmetry between Z and Z bar in the 4 terms.
Yeah, thank you. Sorry.
Oh, it's a good question. Okay, any other? Yeah, what I wanted to say is that, well, I guess I already said it many times, that double trace conformal blocks and their derivatives and the 2 channels give you a basis for the primal space, or for the space of 4-point functions. And the dual basis is precisely the set of alphas and betas that I was introducing earlier. Okay, so this naturally leads to the following set of ideas: the Polyakov Regge blocks. So we can take the dispersion relation and expand it using the OPEs. So let me just remind you that we have, I'll try it like this. So we have the correlator. It's equal to, now we have 3 different expressions for the correlator. One is the S channel OPE, the other one is the T channel OPE, and the last one is the sum of GS and GT, where GS is given by some kernel applied to D disk S, and etc., and same for GT. But because GS comes from D disk S, we can expand the double discontinuity inside this integral using conformal blocks. So let's just take the dispersion relation. Let's just take this formula and expand this, I mean specifically this part, using the S channel OPE, and this part using the T channel OPE. Well, this is what you get. You find that GS is a sum of the OPE coefficient squared times some object, which we called the Polyakov Regge blocks, where the object, this Polyakov Regge block, is just the result of applying the dispersion relation to a single S channel conformal block of the same operator, and similarly for the T channel. So that means that dispersion relation implies that this 4-point function is a sum over all the operators present in any of the 2 channels. Now we are assuming crossing symmetry, so the 2 channels are equivalent, of the sum of the S and T channel Polyakov Regge block. Now that looks like an interesting formula, which which may remind you of the Polyakov Bootstrap. But now, what are these mysterious functions? What are these Polyakov Regge blocks? Well, by the way that they are fixed using dispersion relation means that they are actually uniquely fixed by the following 4 properties. First of all, the Polyakov Regge blocks are single valued in Euclidean signature, unlike conformal blocks. So the S-channel conformal blocks are single valued around the S-channel OP, but they're actually not single valued around the T-channel OP. There are some logarithmic branch cuts. But unlike them, the Polyakov Regge blocks are single valued around both OPs. Second of all, the double discontinuity, maybe let me first explain third point. So third point just follows from the previous slide. We saw that d disk T of GS is 0 and the disk S of GT is 0. So the third point just says that the d disk T of a S-channel Polyakov Regge block is 0. And from that, it follows that number 2, which is that the S-channel d disk of the S-channel Polyakov Regge block is the same as the d disk of the conformal block. And finally, in order for us to be able to apply the inversion formula properly, and hence the dispersion relation, there is a property 4, which says that the U-channel Regge intercept must be negative. So this property just is saying that you can use the U-channel inversion formula for all spins, all the way down to spin 0. And so these 4 properties imply uniquely fix the object to be the S-channel exchange within diagram, exchange of this operator O, plus a bunch of contact diagrams, and these contact diagrams are uniquely fixed by the 4th property. So if you just take the S-channel written exchange diagram of O, you find something which doesn't necessarily have a good U-channel Regge behavior. So and there is a unique way to add contacts to it to satisfy the excellent U-channel Regge behavior. So
these contact terms are supported over finite spins or finitely many spins, or
yes, they are supported in spins. It's strictly. So I think it's strictly less than J of O or equal to J of O. I forgot. Okay. Yeah.
Okay. Fine.
But interesting thing is that they don't share this parity symmetry. So for example, for imagine you take spin 2, O being the stress tensor, then these contact terms, they include also spin 1 contact terms. Like they wouldn't be symmetric under swapping 1 and 2, even though the exchange of the stress tensor is symmetric. But it's forced on you. So crossing, like the full crossing symmetry between ST and U is broken in some interesting way, because we are choosing the U-channel inversion formula, and that leads to the sum over S and T channel exchanges. So the full crossing symmetry is not preserved. Only sort of the symmetry between S and T channel is preserved by this.
Okay, thank you.
So this leads to the following way of thinking about the functionals and this expansion. And let me just reiterate that the expansion says that you can expand the correlator as a sum of certain exchange written diagrams completed by contacts. And this is a completely rigorous theorem, assuming good Regge behavior of G, which is the case in some cases, like when the U-channel OPE. Maybe I don't want to go into that, but in general, you need to worry about subtractions when the U-channel behavior of G is not as good as the property 4, but that can be done. The general idea stays the same. All right, so this leads to the following way of thinking about what I've explained. You can ask how are the Bootstrap constraints encoded from this new point of view. Well, you can convince yourself that the S and T channel OPE of the Polyakov Regge blocks is given precisely by the alpha NL and beta NL functionals. So as I said, PS is some S-channel exchange, PT is an T-channel exchange. So the S-channel OP is going to have the single trace contribution in green, and there are also some double trace contributions. And the double trace contributions have coefficients which are precisely the functionals applied to G of O. I mean, there are different ways to see it. One way to see it is just to say left-hand side is crossing symmetric. It's just sum of PS and PT. So I can apply any of the functionals alpha NL and beta NL to it. And well, I get a sum rule on the OPE. One contribution to the sum rule is just the single trace in green. And the other contribution is precisely the double trace which the particular functional picks out from the sum. So that's how you should, and the minus sign is that they need to compensate each other. That's one way of seeing it. So the way you can think about this constraint is here in the second line, where G is expanded in the S-channel OPE, and that's equal, the equal sign in red, it's equal to the Polyakov-Regge expansion from the previous slide. And let's think about expanding this whole thing in the S-channel OPE. And we can do it because you can actually show that both of these sides of the equation converge uniformly around the origin. Well, the first one certainly does. For the second one, you need to work a bit harder. But you can just expand this around z bar equals 0, and well, what you find is that the right-hand side already contains the single traces, but there are some extra contributions, which are these double trace contributions coming from the alpha and rho, coming from there's the double traces. So the equality of the S-channel OP and the Polyakov-Regge expansion just amounts to the fact that double traces must cancel after you sum over all the primary operators. So this is just a statement that the sum over all the operators of CO squared times the alpha functional acting on G is 0, and the same thing for the beta functionals for all N and L being non-negative integers. So that's the way to derive these equations from starting from the Polyakov-Regge expansion, or equivalently, you can just think of these equations as arising by starting from the good old crossing equation, S-channel OP equals T-channel OP, and applying alpha and beta to it. Those are the old sum rules from many slides ago. But they're entirely equivalent points of view. So these so-called Polyakov conditions should really be thought of as a consequence of crossing symmetry. There's a very nice formulation of this story in Mellin space. Again, starting from dispersion-relation, and then you can sort of impose the Polyakov conditions by hand. But this discussion makes it clear. Well, not quite, but you can show that the Polyakov conditions as imposed in Mellin space are just these alpha type and beta type sum rules, or some linear combinations of them. So really, the point I want to stress is that the Polyakov conditions are a consequence of crossing symmetry, and they are not an independent constraint on the correlator. They're actually equivalent to crossing. If you impose all Polyakov conditions, all of these alphas and beta type sum rules, then their totality is equivalent to the full crossing equation. So maybe let me pause for questions first.
Dalimil, yeah, I was wondering just very naively here. Of course, you, I mean, you took this 5 bar, and so in some ways it was very natural to do it in the S and T channel. But supposing you had identical scalars, then couldn't you symmetrize it, the final answer? And with an extra factor of 1/3 or something. I mean, you'd follow the same logic, write it in the similar expansion, and
you can try doing that, but I think the factors are not gonna work out as one would wish. I just want to add a page. Right, so essentially, you can say that G is equal to sum of PS and sum of PT. And similarly, you could write the same equations for the other two choices.
Yeah, there would be an extra 1/3 factor, which
yeah,
is
there would be extra. There would be extra, and now you could just write, well, G is a 1/3 of G plus G plus G, and sum these three objects. But the problem is, well, what you're gonna get. Oh, sorry.
So get a
well,
factor
essentially, what you're gonna get is a factor of 2/3, right? Because now what happens to the S channel? Let's focus on a single S channel single trace operator. Well, it's coming from here and from here. So there is 1/3 out front, and there is 2. So this sum is going to contain 2/3 of G of sorry, S channel. Right, it's essentially this. Roughly, it's going to contain these type of objects plus some double traces. So if you now equate this with the OPE, you're not gonna cancel the single trace because there's a 2/3 here, but in the SCGP there's just 1 times the single trace. So this idea doesn't seem to work, and it's really I still don't really understand how your type of expansion comes about, like the type which is completely crossing symmetric. It's sort of funny that the dispersion relation leads to this breaking of full crossing symmetry where you just sum over S and T channel, and I haven't really found a way to fix it. It's possible that you can derive your equations starting from these alphas, and I mean, it's for sure, I think, that you can derive your equations from starting from these alphas and betas by taking some linear combinations, but the mapping is not straightforward, I think. So it's still, I think it's still an interesting open question whether one can make a non-perturbative sense of your type of expansion where you sum over all 3 channels.
Yeah, no, I mean, our expansion wouldn't have had this good Regge behavior that you imposed, I think, which because in some sense it's a sort of a perturbative expansion in with these contact terms, which can grow in some this thing way with, but yeah, so it seems to me that that's. You're loosening some things in the assumptions you're making, and you're removing this non-perturbative condition. And so there might be some domain where that's a reasonable expansion.
Yeah. Well, I think just what I want to add to is that you can also treat, using these alpha and beta type functionals and this logic, you can treat also situations which have a worse Regge behavior by doing subtractions. And either you can do it using subtractive dispersion relations, or sort of by hand construct linear combinations of alphas and betas which are compatible with worse Regge behavior, and it's completely clear how to do that. And but in each step you have to fix the Regge behavior, and then you have a set of functionals that you can apply. So
I mean, you want to, that would apply when you violate the Regge behavior by some finite polynomial kind of, finite to some finite extent. But if you have an expansion in contact terms which is sort of growing, then I don't know, that perhaps is
well, in perturbation, at each order in perturbation theory, the Regge behavior is bounded by some constant.
That's true.
So
yeah.
You can,
so you can do it order by order.
Yeah. So I'm sorry that I ran a bit over time, but let me just summarize. So the conclusions are, the main point is that by expanding the conformal dispersion relation of Carmi and Carnot in a series, gives us a basis of nice bootstrap functionals. And nice basically means to have this structure of double zeros on double traces. And the second point is that you can, again, use this basis or the dispersion relation, they're equivalent. You can use it to expand the correlator as a sum of Polyakov Reggie blocks, where these are some exchange written diagrams with contact terms. And the functional basis consisting of alphas and betas is equivalent to the Polyakov conditions, which say that double traces have to cancel in this sum. And then just have some work in progress / future directions is to talk about subtractions, which have to do with the Reggie behavior. Also to sharpen the map to the Malin space formulation, and use the basis to find some nice bounds on holographic CFTs. So hopefully we are going to put out a paper soon explaining these three points. And also I think it would be nice to see if this basis can do better in the numerical bootstrap than the usual basis that people use. I mean, there are some issues with the numerical bootstrap that to really push it far, you need to increase precision a lot. So the question is, maybe this other alternative basis of alphas and betas could do better in some criteria. It'd be nice to try it. So thanks. I think that's all that I wanted to say.
Thank you very much, Dalimil. Let's thank Dalimil. Okay. Questions?
Sorry, Dalimil, Shiraz speaking. This is I'm not sure, legitimate question, but I lost my internet connection about the time you were talking about the upcoming work about the bootstrap bounds and holographic CFTs. Would a 30-second summary be possible?
Oh yeah. I didn't really say much concrete, but the idea just is that, well, you basically need to construct some linear combinations of these alphas and betas, which are positive at large twist. And if you can do that, then you can use this to put bounds on low energy data.
Okay, thank you.
Maybe I can go back to the slide. Yeah, you get this type of sum rule where you have a sum rule between light, you have sum rule including light operators and heavy operators. The positivity on heavy operators means that the right-hand side is uniform, and that implies some inequality type constraint on the light on the effective field theory.
So you hope to be able to constrain effective field theory in ADS using these?
Yes, that's right.
Thank you.
So the Dalimil existence of such a functional would also put a gap on the bound on the twist gap, right?
Mm-hmm. That's right. Yeah. Yeah, but I don't think you're gonna do better than the twist gap function found in the Malin bootstrap paper by Sasha and Joao, because it's saturated. It's the optimal bound.
Right.
Saturated
Right.
bound.
Okay.
Yeah, but it would still be interesting to have such a function in position space. Like somehow the point of view of this talk or of our work is that we like to work in position space. This position space is DispersionRelation and so on.
Yeah.
Their functional is in Malin space. So I mean, I sketched how the two viewpoints are related. I mean, the claim is that they are really equivalent. They are just like a change of coordinates in some sense. So it would still, yeah, it would still be nice to translate that function to position space.
Okay.
So, but let me follow up on that. I thought that the net conclusion of the paper by Penedonis and collaborators and Sasha and collaborators was that it was hard to constrain effective field theories from their point of view. You're going to say you're going to do better. Eventually.
Well, it depends on I'm not sure. Yeah, I don't think that that was necessarily. Well, in that paper they didn't really constrain effective field theories, or field theories in ADS, but I think there is a promise, and the approaches. I mean, the approaches are complementary. Maybe Malin space is gonna give tighter constraints, or maybe position space, but I'm pretty optimistic.
Okay, thank you.
So, Dalimil, if the functional is going to be the same as the one in the melon space, but in position space basis, then the contribution coming from the light operators would have the same sign as what they did, what they had, right? Which in so I guess the striking would be it would be striking if the sign were something that is incompatible with being compensated by the heavy operators. That would be striking. But as far as I remember, they don't find such a thing. They find something that could be
Right.
solved by
Yeah.
heavy operators.
Absolutely, yeah, absolutely. So they have the type of functional where there's like a non-trivial constraint, sort of. Well, in a sense that the low energy effective field theory contributes a non-zero amount, and that needs to be compensated by the heavy operators.
Right.
But the positive constraint is not such that you rule out that effective field theory in that case.
Yes.
Yeah.
But you think that using because I thought you were saying that you would have the same functional but in position space, or do you have in mind multiple functionals and one of which will do even better in that it will rule out certain effective fields?
Maybe. Well, I don't. Yeah, I'm not sure how much I'm at liberty to disclose.
Okay.
I mean, we haven't ruled out anything like that was always believed to exist. So yeah.
I see. No, but still, yeah.
I just think it's like a nice approach to constrain a holographic CFT, but
yeah. Any more questions?
Dalimil, would you mind saying a little bit more about that positivity? I mean, you said something in the beginning, but could you just elaborate a little more about the positivity of the functionals?
Yeah, well, so the individual alphas and betas do not have nice positivity properties in the sense that, for example, when you fix a given beta, then maybe it will be positive for the spin of it's like beta 0, 0. It may be positive for scalars, but once you look at sufficiently high spin, it will no longer be positive. So somehow the double zeros will flip and they will be below below 0. But the trick, I guess the trick is to learn how to take linear combinations of these functionals, which are positive in some sense, like for example, positive above certain gap. Because as long as the name of the game is to take linear combinations such that the n label isn't too large, like so that you still have asymptotically double zeros, but also some asymptotic positivity, and that can be done. It's sufficiently weak constraint, but I mean we still don't properly understand precisely what the space of positive linear combinations is. It seems like if you could solve it, you will really learn almost everything about holographic CFTs, maybe at least at the leading order in 1/c.
So you think that there will be positive functionals which will be linear combinations which will be always positive, I mean, in the regime of interest. So would you say that you should define a basis which is slightly different from the conditions that you imposed, that there may exist a different set of conditions that you impose, which will manifestly give a set of positive functionals? Is that perhaps an expectation?
Yeah, I think that's right. Yeah, I mean, in some sense, the Mellin basis seems to do better from this point of view because the group, the paper by Jo Squared and Sasha found such a function which is positive and has all these nice properties. So maybe the Mellin basis is is the answer, but maybe there's another way to think about it.
Okay, thanks.
Okay. If there are no further questions, let's thank Dalimil again for a very nice talk.
Thanks. Thank you very much.
That was really fantastic, Dalimil. It was very, very clear. Thank you so much.
Thanks.
Yeah. Thanks, Dalimil. Bye-bye.
Bye.